Okay, so moving back to another video. In today's video, we have the following Euler's formula product expansion. So we have e to the power I theta times e to the 2I theta, then 3I theta, so forth, all the way up to e to the power n to the n times I theta, which is equal to 1. So of course, we were being asked to show what the value of theta is equal to such that it satisfies this following expansion over here. And there's not too many comments that I want to make because I think the work shows it in it itself. So basically, I'm just going to jump right into it. Okay, so what I want to notice is that from the expansion we're given, I can actually rewrite this as using our rules of exponents. This is just e to the power I theta. And then this is just we're adding the exponents, so we have 1 plus 2 plus 3 plus all the way up to plus n, still equal to 1. And you'll notice that the exponents 1 plus 2 plus 3 all the way up to n is basically the sum of the n natural numbers. But we know that the expression actually comes down to just n times n plus 1 divided by 2. And now the next thing is that I can actually write e to the power I theta, rewrite that using Euler's formula, dealing with cosines and sines. So then this is cosine theta plus I times sine theta, and then still we have the power n times n plus 1 divided by 2, which is still equal to 1. And then on the right hand side, well, actually not just yet. What I can do now is using de Moivre's formula, I can actually use the exponent and transfer that into the input of our cosine and sines. So really we have cosine of n times n plus 1 divided by 2, and then multiplied with theta. Then plus I times sine of n times n plus 1 divided by 2 times theta, and that's still equal to 1. But now next, what I can do now is that I can actually rewrite 1 in a form using Euler's formula. And basically, we want to rewrite 1 so that it also deals with the periodicity. So specifically 2 and then some value, we'll call that p. So if we just rewriting the left hand side, so this is still the same, and I'm just going to move the theta to the numerator as well, just for the sake of keeping the formatting like clean. So n plus 1 then times theta divided by 2, then this is equal to cosine of 2p times pi, because you do it the 1, and then plus I times sine of 2p pi. And it also should be noted that p should be an integer. So I'll put that down. Now the next step is really easy. Since we both are dealing with cosine and then I times sines, we can basically just set the parts equal to each other. So we can just set the inputs equal to each other. So then that means we have n times n plus 1 theta divided by 2, and we just set that equal to 2 pi times p, or 2p pi, the way I wrote it, whichever. It's commutative under multiplication, so it's fine. So now we can just solve for our value of theta, and what I'll do is just multiply the 2 to both sides. So we have n times n plus 1 theta, and that's just equal to 4p pi, and that last step is just divided by n times n plus 1 to both sides, and then we get that theta is just equal to 4p pi, and then divided by n times n plus 1, where of course p is supposed to be an integer, not an integer, or a set of integers, that way. Okay, and there we have it on this red box like so. Okay, yeah, so it's pretty cool if you ask me.